Howdy, Brian Vikings. We're here to talk about thermochemical equations, and we're going to be looking at page 5 out of our notes. Now, this is really going to be relating chemical quantities to energy quantities, or basically grams to moles. Now, we recall that the units for enthalpy are, well, the enthalpy is delta H, and the units are going to be kilojoules per mole. So the per mole thing is really what we're going to be looking at. That means that we use moles in our reactions so we can relate energy to the moles in the reaction. The easiest way is to start showing you an example. So if I look at example number 9, I have the production of water, and it will have this enthalpy attached to it, which we learned about in the previous video. Now, it is exothermic because it has a negative delta H. Now, the question asks, how much energy would be released if 500, make that 500 with a decimal, if 500 grams of water is formed. So I'll start with 500 grams of water, and I want to see how much energy is going to be released. So I'll change grams to moles because grams are not useful in chemistry, only moles are useful. So there are 18 grams in 1 mole of water, and then I'll be able to see how much energy is released per mole of water. So I'm going to convert my units from moles of water to kilojoules of water, or just kilojoules, I apologize. So the number that I get from this is the number from right here. So I get this number straight that's right here. But there's one extra little hitch because the number on top is going to be 483.6 kilojoules, but the box at the bottom, this number of moles is actually going to come from, not oxygen. It's going to come from the coefficient that's right here. You see the coefficient of water is going to be 2, okay? So I'm actually going to put a 2 right here. All right, that's the easiest way to show that. And when I do my calculation, I'm going to do 500 times 1 times 483.6. I get that out of there. Divided by 18 divided by 2. When I end up with that, I end up with 6,716.7 kilojoules. And this is actually going to be a negative value. That is because energy is being released, so it has to be a negative kilojoules. If energy was absorbed, it would be positive, but if it's released, it's negative. So you need to make sure that you are stopping to think about the last answer that you have. Think about, should it be positive or negative? Does this make sense to be positive or negative? Let's go ahead and approximate this answer to 3 sig figs, since we had 3 sig figs down here at the beginning. So that's going to be 6720 kilojoules. All right, so that's my final answer. I write on my test, yay, I got 100. Okay, so let's go down to the next question. Let me get this out of here. And we're going to look at example number 10. I'm going to get this out of here too. So example number 10 is going to take a look at this. And we're going to have our reaction of going to be propane. It's the combustion of propane. So propane plus oxygen makes CO2 plus water. And it releases 2,219.2 kilojoules per mole. Now, if 5,000 kilojoules, or actually I'm going to say 5,000 with a decimal place to make that 4 sig figs, kilojoules. If that many kilojoules are released, what volume of oxygen will be consumed at STP? So again, I'll start with 5,000 kilojoules with the decimal. And I'm going to change kilojoules to moles this time. Now it's going to be moles of oxygen. Okay, so moles of oxygen. Now the kilojoules, this number is going to come from right here. So that's going to be 2,219.2. And the moles of oxygen is going to come from right here. So that's going to be a 5. Okay, now let me get those arrows out of the way. And then, now I'm going to convert our moles of oxygen to actually liters of oxygen. Okay, so why liters? It's because it said the volume of this. We remember from our gas stoichiometry unit we did in January or February that there are 22.4 liters in 1 mole of gas, any gas at STP. So when I do this calculation, it's going to be 5,000 times 5 times 22.4 divided by 2,219.2. Now, Mr. Russell messed up because this one should not be here. All right. Oh wait, no, that one should be there. I apologize. That should be there. Apologize. So once I do all those calculations, I end up with 252.343 liters, and that's going to approximate to 4 sig figs this time, so 252.3 liters. And now that's my final answer. That's going to be positive. Now, why positive? Because that's going to be a volume. Volume has to be positive. You can't have a negative volume. You can't have a negative nothing. So that makes sense. That's the best way to think about that. As I burn propane, I'm going to produce gas. So I'm producing volume. Example number 11 says that 14.4 grams of magnesium is burned in excess nitrogen at constant atmospheric pressure to form Mg3N2. 136.7 kilojoules of heat is given off. What is the molar enthalpy of formation of Mg3N2? I need to first find my equation, and it says that we had magnesium and it was burned in the excess nitrogen. So excess nitrogen is going to be N2. That excess just means that we didn't run out of nitrogen. And it produces Mg3N2. Now it does say that there are 136.7 kilojoules given off, but that is not the correct thing to write. I should not be writing this in the equation, because if I wrote it like this, then that would be saying that that's how many kilojoules per mole are there. But that's not actually what happens. I'm actually looking for this number because I'm looking for the molar enthalpy of formation of this. This is the number I'm looking for. What it does tell me is it tells me that there are 14.4 grams of magnesium burned off. And for every 14.4 grams of magnesium burned, 136.7 kilojoules are released. So what I'm going to have to do is I'm going to have to take all of this and get all of this junk out of here. And I'm going to show you the easiest way to do this. I'm going to show you that if I just take 14.4 grams of magnesium and I convert it to moles, well, the molar mass of magnesium is 24.3 grams per mole. So that tells me that 0.593 moles of magnesium. It's always a good bet in chemistry to always take any gram value and change it to moles. I'll have to take my energy, 136.7 kilojoules, and I'm going to have to divide it by my number of moles, 0.593 moles, because I'm looking for my molar enthalpy. Okay, my molar enthalpy is going to be in the units of kilojoules per mole. So 136.7 divided by 0.593 is going to be 231 kilojoules per mole. And now you have to think, is this going to be positive or negative? Well, it says that heat is given off. So this is going to be a negative. and that's going to be my delta H. Your homework is to complete the worksheet, Thermochemical Equations. There are 4 questions to do, so have a great day.